All right, my dear friends. Hello, everyone. We have now reached the very last part of indefinite integrals. And in our next session, we will be moving on to definite integrals. So what exactly have we learned together about indefinite integrals up to this point? Let's quickly review everything we have covered. Excellent. The substitution method, trigonometric substitution, and of course, integration by parts. Thank you. We also covered partial fraction decomposition together. In today's session, we are going to summarize trigonometric integrals. I have already covered one or two types of trigonometric integrals with you, but we have not worked on many of their patterns. For this reason, so that those previous types are also included, we will summarize and teach all trigonometric integrals in this section. Is everyone ready? Let's go and be quick. All right, let's move on to trigonometric integrals. The first type of problem we are going to tackle together is an integral that contains an odd power of sine or cosine. I have solved a similar example for you before. What do? Whenever we encounter an odd power of either sine or cosine, we always make sure to separate one factor from it. What exactly does this process mean? It means that whatever odd power we are dealing with, we reduce its exponent by 1 and set a single factor aside, leaving us with an even power. That is right, excellent. So what is our next step then? I do not do anything at all with this single separated factor. This one has an even power, so I will use the first trigonometric identity to simplify it. What was the first trigonometric identity? Sine squared plus cosine squared equals 1. I do not want to spend too much time on this particular point. We want to look at some newer patterns, but let's just do one example, just to make sure we are comfortable and remember how to solve this specific type. For instance, the integral of cosine to the power of 7x dx. We will tackle that together. I will say 1 cosine aside. 1 cosine to the power of 6 remains. I am not going to work with this separated cosine. We will work on cosine to the power of 6. I'm writing down the cosine to the power of 6 and then cosine squared to the power of 3. I'm sure you all know this already. Cosine to the power of 6 means cosine squared. All of that raised to the power of 3. And instead of cosine squared, I'm going to write 1 minus sine squared. Now, what do I have? A parenthesis with 1 minus sine squared, all cubed and multiplied by cosine x dx. Now, what exactly are we going to do? We're going to take the expression underneath the power and set that equal to u. So what is the expression under the power? Sine x. Yes, that's right. We should consider sine x as our variable u. Excellent. Right after defining u, we'll take the differential. Great. The differential is now complete. Cosine x dx is equal to du. So now we'll rewrite the integral. So what do we get? The integral of 1 minus u squared, all raised to the power of 3 du. Now we need to integrate this expression. This whole expression also has a power. Now, what exactly do we have? An expression inside parentheses raised to the power of 3. So I'll expand it using the cube identity formula. Now that we've expanded the identity, we're ready to integrate. Since the integral is with respect to du, we add 1 to each exponent, and then we obtain the result of the integral. Let's move on to the next type. We've already looked at integrals with odd powers. Now we're going to study integrals with even powers of sine or cosine. So suppose we're given a sine or cosine function raised to an even power. What exactly do we do then? Using the golden formula, will handle even powers as well. I've already given you the golden formula and all the trigonometric identities, but I'm bringing this one up again so we can use it here. Let's see what we have in the golden formula. We have 1 plus cosine of 2x divided by 2, which is equal to cosine squared x. Now, if I want to expand cosine squared of, say, 4x using the formula, then in the numerator it becomes 1 plus cosine 8x. All right, now let's apply it. The integral of cosine to the 4th power. Cosine to the 4th power has an even exponent, so we don't need to separate to any terms from it. I'll write cosine to the 4th power as cosine squared, all squared. Yes. Now what do we write instead of cosine squared? The golden formula, 1 plus cosine 2 x over 2. So it became 1 plus cosine 2x over 2. Since the original power was 4, this whole expression will be squared. Now I'll expand the parenthesis. Since the denominator is squared, it becomes 4. I'll take that 4 outside the integral. What do we get in front of the integral? 1/4. What else is left? Open the bracket. The first term squared plus the second term squared is the first identity. Then twice the first times the second. The first term is fine. I'm also okay with twice the product of the first and second because I have no problem with 2 times cosine of 2x. But Again, an even power of cosine has appeared. You see, once again, we've reached cosine squared of 2x. Now we have to eliminate cosine squared of 2x using the golden formula. No need to worry. It's a little long, but very easy. I'm expanding cosine squared of 2x using the power reduction formula. What do I write? Since the argument is 2x, I get 1 plus cosine of 4x divided by 2 plus cosine of 2x. All right, now I'm going to start integrating. Everything is ready for the integration. We had a 1/4 coefficient. Don't forget that. We'll keep that 1/4 outside. What else do we have? I combined those ones in the numerator. We already had that 1/2 there. So now we get 3/2 plus 1/2 cosine 4x. A cosine with power 1 is perfect. Plus 2 cosine 2x. Now we integrate. The integral of cosine ax is 1 over a sine ax. Don't forget the 1 over a. Yes. And just like that, we obtain the result of the integral very easily. Let's move on to the next type. I explained integrals with odd powers of sine and cosine. I also explained integrals with even powers of sine and cosine. What about integrals with even powers of secant? Secant is 1 over cosine and cosecant is 1 over sine. So we begin by separating one squared term. Then for the second function, we use the substitution t equals tangent x. Once we solve an example, it'll become much clearer. And for the cosecant function, we use the substitution t equals cotangent x. Let's solve an example together. It's not difficult. All right, we're going to calculate the integral of secant to the power of 6. So what do we do? Since the power is even, I'll separate one secant squared term. What's left? Secant to the power of 4 times secant squared. Let it stay like that. So I separated one power of 2. And now it became secant to the power of 4 times secant squared. Now what do? I'll set to equal to tangent x. Well, if t equals tangent x, and I take the differential of both sides, what do I get? I get dt equals 1 plus tangent squared x dx. Now you see what we're doing. 1 plus tangent squared is equal to 1 over cosine squared. And 1 over cosine squared is secant squared. So that secant squared we separated was exactly for this. What have we arrived at now? We've concluded that dt is equal to secant squared x dx. So I'll replace secant squared x dx with dt. What was left from the beginning? Secant to the power of 4. I'll rewrite that as secant squared all squared. Why do we convert this into secant squared? Tell me. Because secant squared is equal to 1 plus tangent squared. And we already replaced tangent with t. Exactly. So secant squared becomes 1 plus t squared. And remember, we still have a power of 2 on it. Therefore, the integral becomes 1 plus t squared, all raised to the power of 2 dt. So now we expand 1 plus t squared algebraically using the first identity. So this expression becomes t to the 4th power plus 2t squared plus 1. Now the integration itself is no longer difficult. We'll get t to the 5th power over 5 plus 2 times t to the 3rd power over 3. Yes, and then simply plus t. All right, for the final answer of the integral, we substitute tangent x back in place of t. Very good. All right, let's move on to the next type of integral. Now, we're going to study integrals with odd powers. So now what should we do for odd powers? In the odd case, however, after separating the power of 2, we'll continue using integration by parts. Always, the term with the power of 2 together with dx becomes dv, and whatever is left becomes u. Then Very easily, we solve it using integration by parts. Let's solve an example. We're going to calculate the integral of secant to the power of 3. I'll separate 1 power of 2 from it, so it becomes the integral of secant squared x times secant x. Now for integration by parts, I'll choose secant squared x dx as our dv term. As we said before, we always choose dv to be a function whose integral we can calculate easily. We've calculated the integral of secant squared many times. I told you before, what does secant squared become? Secant squared is equal to 1 plus tangent squared. So what would the integral of 1 plus tangent squared be? Tangent x. So what did we choose as u? What's left now? I am going to take the derivative of secant. What is its derivative? Secant tangent. That's right, good job. Secant tangent dx becomes du. Now, the integral of secant cubed using integration by parts becomes u times v. What was u? U was secant. And what was v? Tangent. So up to this point, we have secant tangent. Then minus the integral of v. And what was v again? Good job, tangent times du. What was du? Secant tangent, okay? The tangents multiply together. And this is what we get, all right? So the integral of secant to the power of 3 becomes secant tangent minus the integral of secant tangent squared. Now we need to calculate the integral of secant tangent squared. What does tangent squared become? It becomes secant squared minus 1. So instead of tangent squared, I'll write secant squared minus 1. And I also have a minus integral of secant cubed on the right side. Now, if I move that term to the other side, what do we get? We get 2 times the integral of secant cubed, which is exactly what we were looking for. It becomes equal to secant tangent plus the integral of secant. And I already proved to you in the earlier sections that the integral of secant is the natural logarithm of secant plus tangent. And just like that, we obtain the integral of secant cubed. So, what are we going to study now? We're going to study integrals where sine and cosine are multiplied together without powers. Normally, we don't know how to integrate products directly, but there are formulas that convert trigonometric multiplication into addition. Look at what this formula says. Sine alpha times cosine beta is equal to 1/2 of sine alpha plus beta plus sine alpha minus beta. Next formula. What is sine alpha times sine beta? It's negative 1/2 times the quantity cosine alpha plus beta minus cosine alpha minus beta. Next case, cosine alpha times cosine beta. What does this become? 1/2 of cosine alpha plus beta plus cosine alpha minus beta. Let's see how we can apply this formula. For example, consider this integral. Sine 3x times cosine 4x. All right, this is a product, and we don't know how to integrate a product directly. So we'll use the formula. Which formula are we using here? The first formula. In this example, alpha is 3x and beta is 4x. So I'll use the first formula. We get 1/2 times sine of their sum plus sine of their difference. But there's an important point here. Alpha must always be the first one and beta must be the second. That means you have to write sine of 3x minus 4x, which becomes sine of negative x. And as you remember, the negative sign inside the argument comes out to the front. I'll simply integrate them. 1 over a minus 1 over a cosine over x. And just like that, the answer is obtained very easily. All right, moving on to the next type. We still haven't worked with integrals involving tangent and cotangent. So when we want to find integrals involving tangent or cotangent, what's our method? Whatever power you have, subtract 2 from it. Then by adding and subtracting terms strategically, we gradually eliminate all the powers. What does that mean? Let me show you with an example. Suppose I want to calculate the integral of tangent to the power of 5. If we subtract 2 from 5, we get tangent cubed. So we write tangent cubed, and then we subtract tangent cubed. Now, again, subtract 2 from 3, add a tangent, then subtract 1. What do we get? We end up with tangent to the power of 5 plus tangent cubed minus tangent cubed plus tangent minus tangent. Now, group them 2 by 2 and factor them. What do I mean by that? From tangent to the power of 5 and tangent cubed, I'll factor out tangent cubed first. What will be left then? 1 plus tangent squared. That looks familiar, doesn't it? 1 plus tangent squared is very important. Now, from the next two terms, what can I factor out? Factor out a negative tangent. What will be left? Again, we get 1 plus tangent squared. Oh, of course, the plus tangent still remains. So now, what do? It's very easy. What do you see underneath the power? Tangent x. Let's set u equal to tangent x. If tangent x is u, then 1 plus tangent squared x dx becomes du. Now, let's rewrite the integral. What do we get? So from the first part, what do we get? U cubed du, excellent, minus u du plus the integral of tangent. All right, u cubed, whose integral is u to the 4th over 4. And for minus u, its integral is also straightforward. It becomes minus u squared over 2. Then only the integral of tangent remains, which we discussed earlier, and you were supposed to memorize. The result is minus natural log of cosine x. Now, we substitute tangent x back in place of u, and the result of the integral is obtained. So what do we do for tangent and cotangent integrals? We subtract 2 from the power, and then keep adding and subtracting terms like this. Let's move on. All right, what are we doing now? We're going to study integrals that contain both sine and cosine, where at least one of them has an odd power. We've already solved examples like this before. Excellent. That's exactly what we used to do. The one with the odd power, we would separate one term from it. So then what would be left? Even powers would be left. Then we would simplify the even powers using the first trigonometric identity. I know we've solved many problems like this before. Let's quickly take a look at an example. All right, now consider the integral of sine cubed, x times cosine to the power of 4x. Oh wait, sine cubed is odd. I'm going to separate one sine term from it. What will be left? Sine squared. I'll use the very first trigonometric identity for sine squared. What was that formula? Yes, instead of sine squared, we write 1 minus cosine squared. So cosine becomes u, and negative sine x, dx becomes du. Now let's substitute and see what remains. So now we have the integral, actually the negative integral of 1 minus u squared times u to the power of 4 du. Yes. Now distribute the parentheses into u to the power of 4. All right, let's simplify and organize everything properly. What we have now is the negative integral of u to the 4th minus u to the 6th. Take the integral, add 1 to the power, and then divide by the new power. Don't forget to apply the negative sign. Well done. Now, we're going to study another integral involving both sine and cosine. But this time, what kind of powers do we have? Even powers. Both exponents are even. Earlier, we said that at least one of them had to be odd. But sometimes, neither of them is odd at all. If the integral involves even powers, we rewrite everything in terms of sine squared and cosine squared. What does that mean exactly? For example, sine to the power of 4 can be written as sine squared all raised to the power of 2. If you write cosine to the power of 6, that becomes cosine squared, all raised to the power of 3. After that, we'll use the golden formulas. Let's solve an example. Okay, we want to write the integral of sine squared x times cosine to the power of 4x. Since sine squared is already in the form we need, we'll focus on cosine to the power of 4. Instead of cosine to the power of 4, I write cosine squared all squared. Now I want to rewrite both cosine squared and sine squared using the golden formulas. How do we do that? We're going to replace sine squared. Do you remember the golden formula for it? It's 1 minus cosine 2x all over 2. Now, what do I write instead of cosine squared? Excellent. 1 plus cosine 2x all over 2. But remember, since this was cosine to the power of 4, we still have a power of 2 on it. All right. This 2 squared in the denominator becomes 4. And together with that other factor of 2, it becomes 8. So we'll take 1/8 outside the integral. What do we have left now? From the first part, we still have 1 minus cosine 2x. And we also have a parenthesis raised to the power of 2, which I'll expand as well. Look at what we get. We end up with 1 plus cosine squared 2x plus 2 times cosine 2x. Then we multiply the two parentheses together. It may look a little long, but it's actually very straightforward. It's just a mechanical process. Now we've completed the multiplication. In the end, we're left with three integrals. One of them is 1 minus cosine squared of 2x. What did we do with that one? Instead of 1 minus cosine squared, we wrote sine squared and then applied the golden formula for sine squared. That's one part. What else is left? 1 cosine 2x still remains. I'm not going to change that one. I'll just integrate it directly. 1 half sine 2x. What's left now? Only one odd power remains. I remember talking about odd powers right at the beginning. I said we should separate one term from them. We separate one cosine term. What remains is cosine squared times cosine. Again, for cosine squared, what do I use? Let's go back to the first trigonometric identity. Instead of cosine squared, I'll write 1 minus sine squared. We'll take sine of 2x as u. Why sine? Because sine is under the power, so we take sine of 2x as u, and then take its differential. Now we substitute. It becomes 1 half the integral of 1 minus u squared du. We've repeated this process many times, and I know you remember it. So now we simply take the integral. We get u minus u cubed over 3, and then we substitute back in place of u. All right, this was the solution to our final trigonometric example. I've given you a complete summary of trigonometric integrals. We discussed odd powers of sine and cosine, and then even powers. We also covered odd powers of secant and cosecant, and then their even powers. We also studied integrals involving both tangent and cotangent, and we discussed problems containing both sine and cosine. I explained the cases where at least one power is odd, and also the cases where both powers are even. I sincerely ask you to practice these examples many, many times. In the next section, we'll move on to definite integrals. Remember, math is all you need.